Well, welcome back after the break, and ready or not, we got to get started on this next unit. This next unit is a continuation of integrals, integration. This unit is integration and differential equations. It is chapter 7 in the textbook, but we only do 3 of the sections there. So if you have a look at the table of contents there, we look at section 7.1, except we don't do all of 7.1. You should note that we don't do the last thing in there, which is Euler's method. So you can omit that from section 7.1. We do all of 7.2. This is about indefinite integrals and integration by substitution, a technique for finding integrals. You'll see what indefinite integrals are when we get there. And I've split it into those 4 sections. But it's not a huge, this is basically the main part of that section and then using it. And then the last thing we do is section 7.4, which is looking back at exponential growth and decay, what you looked at in pre-calc 12, but looking at it from a calculus point of view in terms of rates of change and differential equations that we look at in this unit as well. Other thing to note here is that we don't look at all at section 7.3. That's not part of the Calculus AB course. It's called integration by parts. It's a method of finding integrals that is sort of the reverse of the product rule, but we don't cover that in this course. You'll cover it in a full year calculus course, or if you're one of the few people looking at Calculus BC, that's something you need to look at. And then we don't look at section 7.5 at all. This is another model of growth called the logistic model. We just focus on exponential. All right. Anyways, here I'm going to look at this first section, give you a brief overview to help you get started on learning some of the concepts involved there. So first section, differential equations and slope fields. We'll look at each of them one at a time here. A differential equation, you kind of have already done this. You're going to realize you've already done this. A differential equation, all that means is an equation with a derivative in it. An equation that involves a derivative is called a differential equation. So I put down some examples here. You've seen things like this, right? dy dx equals something. Or you might call it y prime equals something. And you've seen maybe where we started with things where it was just some function of x there, but you can have functions of x combined together with expressions that involve y, or you might even have something like this that involves second derivatives, first derivatives, and so on. We don't get into solving things like that in this course and working with it. While we're talking about it, though, you can think about or talk about the order of the differential equation. It's the order of the highest derivative involved. So this and this are a first order differential equation because they only involve a first derivative, whereas you'd call this a second order differential equation because there's a second derivative in it. All right. This course is just such a brief introduction to this. We just barely kind of scratched the surface of differential equations. And if when you go on to take a full year calculus course, or if you take further calculus courses, you're going to do a lot more with differential equations. So a differential equation, again, just a derivative, an equation that has a derivative in it. And just to start with something like this. Now, again, this is kind of like what you've seen before, except you didn't call this a differential equation, and you certainly didn't talk about solving a differential equation. All solving a differential equation means is to find the functions or relations that satisfy that equation. Or in other words, if you saw something like this, you'd be saying, if that's the derivative, if the derivative is this, what's the original function? Well, the original function, you can just look piece by piece. If the derivative is secant squared plus 2x plus 5, you're going to say, well, the secant squared means this has to be tangent, right? It's recognizing these things as a derivative. 2x is the derivative of x squared, and 5 is the derivative of 5x. The only thing you have to know here that I know you've seen before is there could be any constant added on there, because if when you find a derivative, if we went from this to this, which is a way you can check your answer. You can just check your answer by finding the derivative of this. If you found the derivative of this would disappear. So when you're going backwards here, that has to appear. There could be any constant there. You can call this a family of functions, right? Because it's an infinite number of functions depending on what this is. But that's just a vertical shift that you'll see later when we look at a graph of one of these things. If you wanted to find the unique solution for like some specific value of that constant, you'd have to know a little bit more about this. You'd have to know at least one point on the function. A problem like that where you're given a differential equation and a value, a pair of values, x and y, is called an initial value problem. And when you go about solving that, you get a particular solution. You get one single function. This is a family of functions, like an infinite number of functions, but solving it if you have a specific point gives you that particular specific solution. All right, so here's an example of that. You have this differential equation here, and we're trying to find the particular solution where the graph passes through that point right there, the value 1, 0. So when you go through and do this, well, start by thinking about what are each of those the derivative of. Just kind of work backwards, right? So e to the x is the derivative of e to the x, and 6x squared is the derivative of 2x to the third, right? Again, you can always just double check by differentiating this, right? If you differentiate this, you know, put the 3 in front, 3 times 2 is the 6, and then drop the power down 1 to 2 there, right? And then, of course, you need that constant on there. But now, since we're given this point, we can use it to find the specific solution. This is the general solution, right? It's that whole family of functions, but to find the specific solution, you can substitute those values in 1, 0. So you put 0 for y, 1 everywhere there's an x, and then just start working it out, right? E to the 1 is just e. 2 times 1 cubed is 2. So we've got this 0 is e minus 2 plus constant. So if you move those two things to the other side, well, the 2 becomes positive, the e becomes negative. That's the value of c. You can give it as an exact value like that. If you want, you can give it as an approximate value. I wrote both of those things down there. Probably that's what you're going to see more often is the exact solution. But you could just write it like this as well. And just to understand what we're doing, maybe that means a little bit more to you when you see that. All right, so this is the particular solution for that based on that point and that differential equation. All right. Even if you don't know, we did that one by recognizing what this was the derivative of, right? We said the derivative is this, and we just kind of wrote the function based on recognizing what it's the derivative of. Even if you don't know what this is the derivative of, if this says f prime of x is that, it's a differential equation because that's the derivative, we don't necessarily recognize that as the derivative of something. But even so, we can still write a function. It's just going to be a function that involves an integral, you see down here, right? We can say, well, if we want a function for x, if we want to write a function for x, we can say we know one value here. When we're at 7, the value is 3. So we can start there and say, we're going to take f at 7, and then you've seen that the way you write the change in the value from 7 to x is the integral from 7 to x of that derivative, right? The integral of the derivative of that function is the net change in the function. So this is value at 7 plus the change from 7 to x is going to give our value at x. And so you can put the 3 in there. This is fine as a function. I know it doesn't seem as nice as having an actual, algebraic kind of function here, but if you're using technology to graph it, it works just the same. So before we wrap up talking about differential equations, we should look at some the graph here, graphing the general solution. So this is a pretty straightforward, simple differential equation. The derivative dy dx equals cos x. And so the solution to that is, again, you're saying, what is this the derivative of? Well, it's the derivative of sine x. So the general solution to that is y equals sine x plus c plus a constant. If you wanted to kind of see what that looked like, this is a graph where it's drawn for several values of that constant. So I just drew it for -3 all the way through to 3 integer values. There's an infinite number, but that would be kind of just the whole thing would be green in my case here. So I just drew it with those 7. And you can see they're just vertical translations of each other, right? Which makes sense. This constant on the end here just represents a vertical shift of the sine function. So that constant, that's what it represents there. So that's that family of functions there. And so this visual here, this is a lead into the second part of this section, which is slope fields. If you kind of interpret the differential equation a different way, you could have got a good idea about what the thing looked like without even solving it and coming up with what this solution was. And that's what slope fields are about, which you're going to see here. A slope field is a drawing where you have an array of little line segments on a grid that represent the slopes of the solution curves. That's what a slope field is for a differential equation. And you'll see with the 2 down below here. You can create a slope field for a differential equation without having to solve it analytically, right? We solved the other ones analytically up above. We wrote what the general solution was. But you can create a slope field even if you can't solve it, because some differential equations you can't solve. And that's where a slope field is really useful, right? A slope field, let's, before I talk about it much more, let's see what a slope field is here. So these pictures here, these are just a drawing with little line segments that represent the slopes. So how you're interpreting this is you're looking at this and not saying, I'm going to try and write a solution for that. What you're doing is saying the derivative equals x. The derivative is the x coordinate. So what that means is if the derivative is equal to the x coordinate, it means the slope at any point is equal to the x coordinate. So what you can do is just for an array here, and for this it's just every integer value for x and every integer value for y. At each of those points on this grid here, we're going to draw a little tiny line segment that represents the slope. So you notice here, all of those lines are horizontal there, right? All the lines are horizontal on the y-axis there. And the reason for that is because the slope is equal to the x-coordinate. The x-coordinate here is 0. The x-coordinate here is 0. X-coordinate, every single one of those points is 0. So that means the slope is 0. Right? Next one over here. At 1, the x-coordinate's 1 there, the slope is 1. So these are drawn such that they have a slope of 1. If you're drawing this by hand, like I made this with a computer, I made it with GeoGebra, but if you're drawing this by hand, you just hold your ruler along here so that you're having a slope of 1 there, right? Like that, and then just draw a little line segment in there, right? And the same goes over here. The derivative's the x-coordinate, so all the way along there, they're -1. All the way here, they're -2, right? Those are -2, these are -3, and then likewise on the other side, 1, 2, and 3. Again, if you're drawing it by hand, just, you know, if you want to try and make these that have a slope of 2, just hold your ruler so that it goes like that, right? The way you would draw the slope, 2 over 1 up, right? Just hold the ruler like that and just draw those little line segments there. I know it's tedious to draw it by hand, but just to get the idea of that. All right, the second one here, dy dx equals sine x, means the derivative is the sine of the x-coordinate. So the slope at each point is equal to the sine of the x-coordinate. So this one you have to do a little bit of thinking here. At 0, so all the way along here, the x-coordinate is 0, and the sine of 0 is 0. So all the way along there, they all have slopes of 0, right? All the way there. And then maybe another place, or a couple other places that you might know. You might also know, okay, sine of pi is also 0, and sine of 2 pi is also 0. So I know that all of those things, the slope is going to be 0. So you have slopes of 0 all the way down there, right? All the way down there. And then these are all slopes of 0 as well. And then negative pi, right? The value of the sine of a value, sine of the x-coordinate is 0 everywhere, 0, pi, 2 pi. So all of those are going to have slopes of 0. And then if we keep going here, if this is pi over 2. So pi over 2, sine of pi over 2 is 1. So these are all slopes of 1. Now it's harder to draw these by hand as slopes of 1 because the grid is not, like over here the grid was 1 each way, so you could use your ruler like that. Here it's harder because this is about 3 here, right? And this is 1, 2. So getting a slope of 1 is kind of hard there. So you could just kind of approximate it with a line going up like those ones. And then when you get to this value, 3 pi over 2, the slope is -1, so you can just draw them so that they're slopes of -1 and so on. And then this same thing, -1 over there. If you were really doing some analysis with this, you would be using a computer. But I'll leave it till the end of the video to show you how to use a computer to do this. But you won't really have access to that in, if you're taking the AP exam. And realistically, taking the AP exam, if they want you to draw a slope field, they won't give you nearly as many lines as I did here. They might give you, 15 or 12 in the middle here, and just to get the idea that you know how to draw one. So I wouldn't worry too much about it. Now you notice that I've got this orange curve here and here. Now what that is what I have down here, which is you can use the slope field to kind of see what the curves might look like, right? The solutions, right? All we did is we just interpreted this as what the slopes are going to be. But you can see from this, well, this sure looks like, these start at 0 here and then they start to go more up right here. So you can tell the curves are going to be these upright parabolas like that. And you can tell for this, well, we've got 0 and then it's up here and then it's horizontal, it's down and then it's horizontal. If you kind of follow the slopes of the little line segments, and if you imagine that if you imagine you drew more of them, like we drew them for every like integer value here or fractions of pi, but if you had ones in between there, they would start to go up here, they would start to go horizontal again down there, and so on, right? You'd get that curve like that. So these 2 orange curves here are the particular solution that pass through this point. F of 0 is 1. So in this case, when f of 0 is 1, you pass through that point, and then you recognize it's going to go up from there, and you recognize it's going to go up from there. So you just do your best to try and draw the curve through there, right? And the same thing with this. If you're going to pass through this point, you know it's going to start to slope up because these lines are positive here, right? So it starts to slope up to the right, and then it's got to get to that kind of symmetry-wise there again, right? And then it's got to go down, and symmetry-wise, it's got to be horizontal again there. So you just kind of draw a smooth curve through that the best you can. That's the particular solution. The slope field just gives you a sense of what the curves look like, all right? So again, slope field, the idea is the line segments that you draw suggest how the solution curve goes, all right? Let's look at another one here. Sometimes differential equations can have expressions involving both x and y, like you saw at the examples I showed you at the beginning. If you're working with something that has x and y, so like this one here, dy dx equals -x over y. So you can interpret it the same way, right? The way we did. To try and draw a slope field, the derivative is -x over y. So how you're interpreting that is the slope at each point is the negative of the x-coordinate divided by the y-coordinate. All right, negative of x divided by y. So if you want to draw these line segments, again, I used GeoGebra to generate this, but if you're drawing them by hand, pick any point and draw line segments where what you've done is you've said, what's x divided by y, and then make it negative, change the sign. So let's start with these ones all along here. Everywhere here, the x-coordinate is 0. The thing on top is going to be 0. right? Everywhere there, the x-coordinate is 0. So when I go 0 divided by whatever y is, it's going to be 0. So all of those are 0 slopes, so they're just horizontal line segments there, right? And then beyond that, we can try and fit some other ones in. You don't necessarily want to go like left to right here like you're reading a book. It's better to look for places where there's going to be common patterns, like recognizing, hey, when that's 0, all of these are going to be 0. Or you might also say, well, what about if x and y were the same? If x and y were the same, like 1, 1, 2, 2, 3, 3, negative 1, negative 1, negative 2, negative 2, negative 3, negative 3, well, that would be something divided by itself as 1, and then that negative makes it negative. So all of those are negative 1. And then if similarly, right, if these were opposites, right, like negative 1, 1, negative 2, 2, negative 3, 3, 1, negative 1, 2, negative 2, 3, negative 3, when you divide those things over here, it gives you a negative 1, but then that's going to make it positive 1, right? Negative 1 is positive 1. So all of those are positive 1. Again, just if you're using a ruler, you can kind of hold the ruler up like that to kind of hold have a slope of 1 like that, so you get it kind of right. The other ones are similar there, right? The other ones, if you look at, this is 1, 2, right? So this is 1 over 2, but negative, so it's downhill, right? This is going to be the same thing right here, right? Negative 1, negative 2. Negative 1 over negative 2 is 1/2, negative 1/2, right? That's negative 1/2, that's negative 1/2. These are both positive 1/2 for the same reason. The other ones, every time you just take the x divided by y and change the sign, right? So hopefully that makes some sense to you there. Once you start seeing the thing, and maybe actually before we start looking at what that is, one other thing you notice is there's nothing drawn here along there. GeoGebra does draw something there, but the convention is that you don't draw something there because everywhere there y is 0. So when y is 0, this expression is undefined. The derivative is undefined there. So you don't draw any lines there. In reality, what it would be is those lines would be vertical in this case, but we don't generally draw them when the slope is undefined, when this expression is undefined. So that's just a slight difference. On GeoGebra, again, it draws them, but that's only because it's just doing a calculation of some sort, so I would just disregard that. Again, here we're asking, let's draw the smooth curve through the particular solution that passes through 0, negative 2. 0, negative 2 is this point here. And you just have to, as you start to go up maybe, you notice that they start to slope to the right. And just again, by symmetry, it should pass through there. And as you keep going, by symmetry, it should pass through there. And by symmetry and so on, right? All the way there. And you can make out a circle by the end of that thing, all right? Now, something we didn't do with the other ones, we could have, but we didn't, was solve it analytically or algebraically here, solve the differential equation analytically. We could have, as I said, for these two, right, you could write what that is. If dy dx is x, I'm pretty sure you're okay with saying, well, if that's the derivative, then 1/2 x squared, right, plus a constant is the general solution to that. And so that's a parabola, which makes sense for what we had here. And if we did this, we'd say, okay, we know that sine's the derivative of minus cos plus a constant. If you look at that, right, this is a minus cosine curve up to, those are all minus cosine curves depending on what the constant is there, right? We could solve them, and we could actually solve them with that initial condition. We didn't here, but we're going to do that now for this one because this is a little bit more tricky to think about here. If we want to solve this one, so this doesn't just involve x. If it has x and y, the way you can solve it is to separate the x and the y. So write these separately on either side. So I'm going to leave the minus x on this side, but I'm going to multiply both sides by y so that it's over there instead. Because then I've got minus x and I've got y dy dx. So it's not like before where it said dy dx is something. But what we can do, just like we did before, we said if this is dy dx, we want to recognize this as the derivative. We can still just recognize both sides as the derivative, right? If that is the expression on the right, that's the derivative of minus 1/2 x squared plus a constant, like we just saw on the previous page. This is trickier, but it's y times dy dx. What that is the derivative of is it's the derivative with respect to x, of 1/2 y squared. Y times dy dx. With the chain rule, if you think about it, if you were trying to evaluate this, because you can always just work backwards to see if you got it right, d dx of 1/2 y squared is, 1/2 y squared. Put the 2 in front, multiplies by the half to get 1. Drop that down 1 to 1, so you get the y. But then since that's not a y, you got to have dy dx there. All right. You're going to do more with this later and have more formal ways of solving these. But right now we're just recognizing each side as the derivative of something. All right. Now you might say, how can we put a constant there but not there? Because I don't need a constant on both sides. I only need one constant, because if I put a constant on each side of this, if I put a constant on the left and the right, you could always just combine them. Like let's say one constant was plus 7 and the other one was plus 20 over here. Well, you could always just move this one over and make it plus 13, right? So you really only need a constant on one side when you're working with things like this, all right? Now, I took it up here to work with this to find the particular solution that we had here with 0, -2. I moved this negative a half x squared over to the other side, so we've got half x squared plus half y squared as a constant. What I did next is I multiplied everything by 2 to get rid of those halves, so I just have x squared plus y squared. And you might say, rightly so, why didn't you change that c to 2c? Well, this is why. Because if this is any value, this is any real number from -infinity to +infinity, if I multiplied it by 2, 2 times c is still just any number from -infinity to +infinity. This just represents any number. This still just represents any number. If you really wanted to and it bugged you to do that, you could call this one C1 and call this one C2 or something like that. But you really don't have to, because this, we don't know what it is yet. It's any real number. And this is still just any real number. Anyways, if you keep going with that and substitute the two values in, 0 for x, -2 for y, square both of those things, you get 0 plus 4, which is 4, so the constant's 4. So you got x squared plus y squared is 4 there. And if you look back at the picture, that's what that circle represented, right? X squared plus y squared is 4 is the equation of that circle. All right? Let's move forward here a little bit. This equation that we did here before we move forward, this differential equation here is one that you call a separable differential equation, because I can separate these, the x and the y there, the expressions involving x and y. I can separate them so that there's the y expression on one side, the x on the other side. You can have differential equations that you call not separable. They're non-separable differential equations. And here's a simple example of a non-separable differential equation. It's non-separable because you can't separate the things, the x and the y. Now you might say, hey, that looks simple enough. Why don't we just move this to the other side? You can move it to the other side, but if you have y plus dy dx, we can't recognize that as the derivative of something that's going to allow us to solve this. And the algebraic methods of solving non-separable differential equations, that's a topic for a full year calculus course, or even beyond that, a later calculus course. So we won't worry too much about that here. You can try, if you want, try separating it and looking at each side as the derivative. But this is where a slope field is really particularly useful because, again, you can interpret it. This is no harder to interpret than the previous ones because all you're saying is the derivative is x minus y. So the slope at every point is the x coordinate minus the y coordinate. So that one's actually not that hard to do. Again, I would say don't work left to right here because it's going to take you way longer if you're drawing it by hand. Look for places where it's going to have some commonality. So x minus y, right? Think about, okay, if x was 1 bigger than y, that would equal 1. Or maybe the best place to start is where x and y are equal, the slope's going to be 0. So where x and y are equal, 0, 0, 1, 1, 2, 2, 3, 3, all of those have a slope of 0. So I would draw those first. And then where x is 1 larger, like 1, 0, 2, 1, 3, 2, 0, negative 1, and so on. All of those are going to have a slope of 1. And you can continue to the right. All of these are going to have a slope of 2. All of these are going to have a slope of 3, 4, 5, and that one's a 6. If you go the other way, right, if you go these points here, right, negative 1, 0, 0, 1, 1, 2, 1 minus 2 is negative 1, 2 minus 3 is negative 1. All of those are going to be negative 1. And then so you can continue. That's going to be negative 2, negative 3, negative 4, and so on. So look for patterns if you're trying to draw these by hand. Definitely. All right. Now, where's the slope 0? As we said, it's along this line y equals x because the x and y are equal there, so it turns to 0. This slope field has a feature that the other ones didn't, right? How is this one different than the ones in the previous example? The feature that it has is there's this line where the slopes are all pointing straight at each other, all right? This is actually an asymptote. This graph has an asymptote there. The line y equals x minus 1 is an asymptote. Because when we're trying to draw a curve, like if we're trying to draw this particular solution through 0, 1, if we're trying to draw the curve through 0, 1, there's 0, 1. Well, it's going down, but then as you can tell, the lines become 0 here along this line. So, right, along that line, it's got to be going horizontal here, right? This has to be horizontal along that line. And then as I go to the right, they're going up, right? So it has to start curving back up again this way. But it's not going to reach this line because the closer you get to that, right, anywhere before that line, right, it's 0 here, and as you go to the right, it becomes 1. But anywhere before that, it's not quite 1. So it's always going to be a little bit less than 1 there. So it's always going to get closer and closer to that line. Conversely here, if you started on this, you'd never get off of that line because you'd follow that slope, you'd follow that, you'd be on that line, you wouldn't get off of that line. So that has an asymptote. It's an interesting situation. Again, we don't do anything really with non-separable differential equations, but just for the sake of completeness, I thought it'd be good to look at that, all right? And again, as I said here, why can't this be solved analytically? We haven't really done much, but if you try to separate the expressions, variables, you can't separate them such that you can recognize each side as the derivative. You can try it to convince yourself. There is a way to solve that analytically, but that's a topic for another course once you have a method for solving that. Really, in a differential equations course. You can take a whole course in differential equations if you want. All right, so that's an intro to that first section. Hopefully it helps you get started. Remember that I said we don't look at the third thing in section 7.1, which is Euler's method. So when you're looking through the textbook examples in the practice, anything that talks about use Euler's method to do something, not doing that, right? All right, that's it. Do some practice, and I'm sure you'll be fine with this, right? And maybe before we're done here, we'll have a quick look at how you can generate a slope field on GeoGebra. Now, the reason I don't use Desmos for that, I know lots of you use Desmos, is because it doesn't have a built-in slope field function. There's people who've created things using Desmos that generate slope fields, web pages and stuff, but There's no built-in thing. So GeoGebra does have that. If you just Google GeoGebra, you'll find it. You get to that page, start the calculator. Looks very much the same. And the easiest way to find things on GeoGebra is just to start typing. So if you know that you're looking for something called slope field, just start typing slope when you see that, and then you find the different things. It has a number of different things where you can draw a slope field. I'm going to use this one here because it lets me put in a minimum and a maximum. If you didn't put that, it would just cover the whole grid with it, which you could do if you just put some of the other ones there. If you just do slope field x, f of x, y, it'll just cover the whole grid with it, but I'm going to use this one. This fxy means that's the expression, like dy dx equals negative x over y. That one we have, you put in here negative x over y. The number is how many you want from left to right based on what you put in here for a min and a max for each of x and y. It's a bit of a weird order: min x, min y, max x, max y. And then the only other thing here, length multiplier. You put a number in for how long you want the little line segments to be, which you can see in a second here. So if we're doing this, I'm going to put the one we did, minus x divided by y. I am going to put in here the number. I'm going to just go from, like we did, -4 to 4 before, and I want one every integer. So I'm going to say I want 9, and I'm going to put that I want the length. I'm going to put, I'll put 1 in here. That's not what I use because that draws the lines a lot longer than the ones I had. And I'm going to go minimum x -4, minimum y -4, maximum x 4, maximum y 4, and you see those lines are pretty long. So what I did is I went back and changed it after to something else. So I just put 1 as the length of the line. You could put in 0.5 or something, and then they're shorter, and so on, right? So that's how you can do a slope field. As I said, if you didn't have the mins and the maxes, it would cover the whole grid. So you can play around with that if you're interested in doing that, all right?